think I will begin after this long break. We'll let me review where we are. First of all, this is a course in differential geometry. You all know that. And the first object that we studied interesting object at least for me, or objects, connection on vector bundle. Maybe we give the vector bundle some notation, the usual projection from the bundle space to the manifold. And of main interest, is the case when the bundle itself is a tangent bundle. And as we will see today, and associated bundles to the tangent bundle, what you physicists would call tensor bundles, but just for today, let's talk about the cotangent bundle would be important. So a connection is usually denoted by nabla. It's a mapping, and it takes a derivation on the C infinity functions, which is the ring of interest here. Prof and some other people have been interested in algebraic geometry, so this is really a sheath. But just a global ring of C infinity functions. And you get a first order differential operator on the bundle. Well, on sections of the bundle. And you write it all out. So this guy here is just the vector fields, in our case. And the notation is nabla, the classical notation, nabla sub x. You take x to the operator nabla sub x. And the differential operator condition is nabla, it acts as a derivation the obvious way of f times the section is f times the derivative of the section. So this is the derivation condition, x of x times the section. Now, we will discuss curves in M, and usually these curves are local. So not a global, usually, let's say at first in our discussion, they're local. So we don't worry about global phenomena at first in a coordinate chart. And I denote a curve by a mapping from an closed interval, but defined in the neighborhood of the closed interval into the manifold. And in coordinates x1 through. And now I try to be consistent with both physics and differential geometry. Put the index upstairs on this. People who work in indices learn good conventions, so you should just copy their conventions. I just copy whatever my physics friends tell me because physics notation is always the best. Don't smile, I mean, but it's true.
They were complaining the other day.
Yeah, but it's in fact true. It's in fact true. No. But then mathematicians have to tell you what your notation means. Okay, so in coordinates that's, so gamma of t is x1 of t. Xn of t. It's the manifold is one-dimensional. So in this local situation, we're in a coordinate chart and we have a smooth curve. And so at least piecewise smooth. And with one exception, almost always smooth. So we have some curve in a coordinate chart. Here's a gamma of A, and it goes along here to gamma of B. And at each point you have a velocity vector, which we write as gamma point at time t. And we, because this is in a coordinate chart, we can write it as x point 1 of t to x point n of t. That's the derivative, but as a differential operator, really we should think of it as a vector field on the curve gamma of t then is the usual thing, x point I, and now we drop the summation sign always of t d I. That's the short notation. Okay, so that's a vector field along this velocity vector field along there. And if we have a vector field V, say equals V of t, is a vector field along the curve. Gamma of t. This is abusive notation. Really, this means V at the point gamma of t. Right, but we write like that. We can have a vector field along the curve. And this is one of the key things to understand. We have this vector field along the curve. And maybe it starts out like this and it's changing along the curve. I don't know, something like this. So this is the vector field V along the curve. And now we can differentiate that vector field along the curve. That's the whole point of this thing, or one of the main points of this thing. So we differentiate V along gamma using the connection. Now, so how do you do that? Because don't forget, connections are only defined on global vector fields. So you have to extend the vector field nearby to a vector field near the curve in a neighborhood of the curve. So the image of the set, to be precise here, so you extend it nearby. We have a picture like that. Here's the curve, gamma, and then you start, you're given the vector field on the curve, and you can extend it. It's very easy because locally this is just a product. So you can extend it to a vector field nearby in some neighborhood of the curve. So I'll write it again as V as a vector field. Now, your author, Lee, his name is Lee, the book that I suggested to you, allows only piecewise smooth, so you have to worry about what it means to extend at corners. But it's the obvious thing, so there's nothing to do. Okay. So that's what you do, and you differentiate it, and the answer you get is the derivative of this thing, V along the curve, gamma of t, is denoted by your author, whose name is Lee, as dt of the vector field V. If you like, you can put V of t. He calls this dt along the curve. Yes.
So beneath the number, is that supposed to be gamma?
We're different. Oh, thank you very much. I haven't said x equals x. Yeah. So I'm sorry. Yeah. So thank you for the remark. He doesn't know what x is because I haven't told him. But what is x? Of course you know. You just reminded me. And you have gamma of t here, differentiated, and you have to extend this also to really make sense out of it. But it really does. Nothing depends on any extension. So okay. So that's really just gamma point along. So on the curve. Thank you. And let's compute it. So this says nabla of gamma point of V. I hope I did, what is V? Is V around here? No. So let's call this V J dj. And this thing is x point j I di. So for the mathematicians here, physics people will laugh at us because they can do this in so fast. We have to do it slowly because we are stupid. Okay, but remember that this is a derivation, and remember that everything is linear. This thing is linear over the functions, and this thing is linear over the constants. That's the way to think of it. So this thing is first of all, you apply the connection to Vj. So it is, well, let's write it. It's x dot I di. Let's see here. And that, well, let's put Vj here. Di applied, oh, everything's upstairs, applied to dj. Maybe I should write this carefully. Nabla di of dj. Right? That's di applied to dj. You should think of this whole business as taking a vector field and letting it act on sections. You want to know how it acts on sections, it's like group representation. So this is, the Nabla tells you how this vector field acts on that. Right? That's that plus something. And what we know here is this guy here is Christoffel symbol that. Right? That's the definition of the Christoffel symbol, so that gives you the connection. Right? This is virtually anything. And now we have to differentiate the coefficients of the VI. So, of course, it's linear in this thing, so it's the xi dot. Now we have to differentiate with respect to this guy, the coefficients of Vj. So di of Vj, right? That's what I have to do when I'm differentiating with this thing. Now look at that. Vj of t really means Vj at the point gamma of t. Right? That's what it means. And when you differentiate it, this is the point Vj of x1 of t to xn of t. And when you differentiate it, you use somebody's rule. Maybe it's called the chain rule. Right? You differentiate the outside and so on. So look at what we have. This is the inside derivative and this is the outside derivative. Right? So I'm tired of this thing. I just call this Vj point because that's all it is. Right? And I don't like this thing because I had, okay, Vj point. Okay, I'll write it here, dj. No. What do I have to write it? Yeah, dj. Right? Okay, but I don't like that because I have a k here, so I'm going to change that. So I'm going to write this as gamma point, x point, Vj gamma ij k plus Vj point. What's Vj? Yeah, Vj point. Yes, I'm Vk point. Now I want to use the same index here. So Vk point, Vk. Yeah, because I want to use the same index there. Right. See, I'm a master of this physics stuff. You don't like it? Oh, you're happy. Did I make a mistake already?
Yes.
What?
The indexation of V should be up.
Oh, the index is supposed to be up. You got me again. This is terrible. Okay.
Yeah, this is
Okay.
DIVJ also should have the index up.
Huh?
DIVJ. So before that. DIVJ. So x dot with an upper index I. Now before that. To the left. Left more. Yes. So VJ is with that.
It's great to have people like that here. I never make a mistake. Okay? And anyway, I shouldn't do it like this. I should put the bracket here and have dk. Right? dk is down? Oh, yeah, these guys are down. The operators are down. See, you see, I don't know who invented this notation, Christoffel maybe. But what he did is he made notation so the idiots can do it, excuse me. I have many people who study mathematics with me who have to have physics as a second subject. And what they all tell me when they have to pass physics exam is, don't think. But there's a point to that, right? Just once you get used to the notation, don't think, just do it. Yeah, it's true, it's very good, and I admire physics people greatly for being able to do it. So finally, after many minutes of work, we have the precise formula, everybody's happy, for differentiating a vector field along a curve. Yeah. And we say V is parallel along gamma. Means that this guy kills it. So no indices. So I can't make a mistake.
So that X,
Oh, I mean this. Oh, here's another guy.
that X star line should be outside the bracket.
Where? Here?
That X star line should be outside.
Oh! No! Ha ha ha! Ha ha! Ha ha! You made a mistake. Right? You see what happened here. Right here, what this is something like, what's it called? The inside-outside rule, the chain rule or something like this, right? I applied the chain rule. Okay. Great. I'm glad everybody's happy now. So, I'm happy. Okay, that's really nice, right? So, as you see, this is an ordinary differential equation. Right? And so we talk about parallel transport. As this, you prescribe at the beginning point, or some point, doesn't matter, beginning point, y and gamma of A, that's prescribed. So this is the initial value. For the ODE. So this is, yeah. So what does it mean? What's the ODE? Well, the initial value of y, and this is the initial point. Right?
Who is Y?
Hmm?
Who is Y?
Y? Yes, this is a good. What is y? She's upset because she doesn't know what is y. So, I wrote down ODE and you were happy with it. You should have yelled at me then because that's just some equation. Given y, this is how you differentiate, and you define this thing to be parallel if that thing's 0. Now I'm going to say, regard this as an ODE for y. Okay? With y being unknown. So OD is a very good question, right? What is y? ODE for y. I didn't say it, right? So y being unknown, I want to find y along the curve, which is parallel in that sense. That's an ODE that requires initial values. Initial values for first order ODE is the point and the tangent vector, right? You okay on that or not?
Where is the y there? I mean, it's
Oh, probably, maybe, maybe that's what you meant by y. Where is y?
he probably means b.
Okay, now everybody's happy. That's probably also what you meant, but both things you meant probably, okay? I don't know, when I think about this thing, I have several notations in my head. And I try to change to your book, and your book is V. Okay, but your book is not my book, so that's my problem. Okay, so please correct me on this. It's even good that you correct me like this, right? So this is ODE for V. Regard V as unknown, and you want to know what it means to parallel transport an initial vector, which is an initial point and an initial vector in the bundle. I'm thinking here the tangent bundle, but in any bundle. And that solves the equation. So this is the parallel transport and now thank you very much, of V at gamma of T0 along gamma. Okay. And as I've said, you could use parallel transport to differentiate. That's what you do in beginning analysis, right? You bring it back by parallel transport, you subtract off the value there, you divide by what you took, the time, and you get the derivative. That's exactly what parallel transport does for you. Okay. Now, that was a little bit of a review. That's what differential geometry is at the beginning. It's just calculus with an additional structure which is called a connection. So a warning, the space of connections is very, very big. Is infinite dimensional. It's really not a warning, it's just a remark that you need to take into consideration. There is no good connection. God doesn't come as no God-given connection. There is no such thing. God doesn't say today we use this connection, tomorrow we use that. There's no, it's just, we look for good connection. Keep in mind my Japanese friend who told me all the time, Alan, many connections. Go find good connection. That was what this is the goal. What is the good connection? So an interesting equation gamma is parallel to itself. Yes? That means that if you move along gamma, the field of gamma doesn't change. Parallel transport. This means it's straight. You should think of gamma as being straight. Of course, with respect to the connection. Because it moves, it doesn't change with respect to the connection. With respect to parallel transport, it doesn't change. So this is this condition. This is the. I'll write it here. This is the differential equation for being straight, and we call this the geodesic equation. But let me emphasize with respect to the connection. Of course, with respect to the connection, but all of us who travel in airplanes believe that the geodesics are with respect to the metric, right? The shortest distance, but this is with respect to staying straight. Okay, so this equation, of course, this ODE is, let me try to write it, there it is. So it's just that Vj is equal to, I forgot it, there's a point here, right? And you probably got me all upset if I made a mistake. So the geodesic equation is this, x dot I, and now Vj is also x, so it's x dot j, gamma ijk, plus the second derivative, so Vk is xk, Vk dot is xk dot, so this is x double dot k, Vk. All I did here was put in Vj equals x dot j. That is the equation for the thing being straight. So that is a second order ODE. Okay. Now everybody here in high school learned how to handle second order ODEs. Okay. For example, I will remind you of how to handle a famous second order ODE. So an example of a second order ODE. X dot, I forget the notation, one variable, x dot dot, plus, let's make it even, I don't know, let's even make plus minus here and think about it. It's very interesting because sign starts to matter. Lambda x equals 0. This is my favorite first example of a second order ODE that you learn in high school. Right? And you also learn in high school how to handle it because this is second order. And what you do here is you let u equal x and v equals x dot, and this thing becomes v. Okay, you write it down. U equals x. So I hope this. U dot equals v, and v dot equals u. Or probably minus u. Well, it depends on the sign. Wait a minute. What does the sign mean? If I bring this over on the other side, what do I get? V dot equals minus plus u.
That's a plus minus there, even though they're not equal to.
Pardon?
That's a plus minus there, no?
That's what I mean, but I wanted to emphasize that it really matters what the sign is. The sign is the sign of the eigenvalue. Right? It has to do with the frequency of this differential equation, right? So this says that uv dot equals some matrix times uv. Oh, I gotta put a dot here. And uv dot is that, so that is this, right? Well, let's have fun. Let's make this plus, and so this is minus. This is my favorite matrix. Right? From make that plus, then this becomes minus here, and that's my favorite matrix. You know that's my favorite matrix because you learned from me complex analysis. So this is J times EV. Okay. And you know, this is a linear ODE, and the solution is a one parameter group e to the t j. Right? And what, yeah, are you familiar with this? You should be familiar with this. You had Caven's course, you had Caven's course, you had Caven's course, you had Caven's course, you had Caven's course. The solution to a linear ODE is the associated one parameter group e to the t a, where a is the operator that defines the one parameter group. Okay? This is something that, in my opinion, is missing in the elementary courses of analysis -1, and the reason is, in analysis -1, you don't have linear algebra -2 available, right? And in linear algebra -2, you write down this kind of thing. It's a beautiful thing, right? A power series development in an operator. It's a beautiful thing. So that means well, if we call this thing a vector, I don't know, a vector W, and so this is a vector W point, so this is the solution, and this orbit is the solution with initial value W, say maybe W0, which is the initial value of the pair U0, V0, well, is initial value U0, which means the point and the derivative. So a second order ODE requires an initial value of a point and the derivative. And the solution is, in this case, the orbit of a one parameter group. And in general, so the general theorem solution of a first order ODE is the same for the vector field, for a vector field X on the manifold, and is at initial value, let me just write just in the same notation, W0 equals Gx of t, the orbit of the point W0 by a one parameter group. And now I lied. Every physicist thinks I don't lie because they think, you probably think every one parameter group is global because in your one parameter groups they are global, but this is a local one parameter group. You got it? It's not globally defined. You understand? Vector fields are not globally integrable, right? They're only locally integrable by local one parameter groups. And the domain of integration depends on the point. So I hope you have this picture in your head. Depending on the initial value, you can integrate a certain time. Yes? And so this is the orbit of a local one parameter group.
What do you mean integrable, as in on the curve? For the vector field to be integrable, you mean on the curve?
I mean that these are the integral curves of the vector field. I mean, and this is a big point that almost everybody misses, and I want to scream at you to please don't miss this point. Yes? Yes? To solve an ODE means to find a local one parameter group, period, comma, out. It does not mean find a curve, an integral curve. It means to find a local one-parameter group action. It's precisely the same thing. Okay. Some people formulate this, the solution depends differentiably on the initial condition. You've heard that. The solution depends differentiably on the initial condition. But if you have a local one-parameter group, that statement is stupid. That it depends differentiably. Everything inside here is differentiable. Okay? A vector field and a local one-parameter group action is the same thing. Okay? Please get it in your head. So if you have not done this, I'm really serious about this, please take the book of Arnold and read it from cover to cover. So the literature is Arnold ODE book. And you're always asking me for literature. That is a book written by a great mathematician, student of Kolmogorov in the great Russian school of the 20th century. A fantastic mathematician with great expository abilities. Read everything that this guy ever wrote, if you have a chance. Don't read modern abstract nonsense. Read what this guy wrote, particularly people interested in the overlap with physics and mathematics. The Institute of Mathematics in Moscow, NUMA, is in some sense together mathematics and physics, in the old sense. Yes. And you think of not just the ancient Russian mathematicians, maybe Maltsev and some in the 19th century, think Kolmogorov. Okay? He is responsible for a huge portion of 20th century mathematics. Okay, Arnold's ODE book I recommend. I will tell you something. I almost never like to read. I'm not lazy because I'm too proud. I see a result, I want to prove it myself. But I was giving a course once in Italy, and I told the students, read Arnold's book because I knew it was a good book. And then I started looking at it, and I could not put it down. Okay? This is his elementary book. We call it his elementary ODE book. Okay, so we have an elementary ODE. We go to, this gets transformed to a first order ODE. Alright? I'm sitting down because when I was first a student in high school, I forgot, I looked at this and it said, this is great, you get J, and you get this E to the TJ, that's a wonderful thing, a power series and an operator, and you differentiate, you get the solution and so on. And I forgot to ask, well, what in the heck is going on, right? Where is this ODE defined, right? This is just some letters, U and V, right? U and V, it's always U and V. Right? U is U and V. So the first order ODE is defined on the tangent bundle. Right? Is it not? Excusez-moi. This is U equals X and V equals X dot. This is an ODE on the tangent bundle of the manifold. So the connection geodesic let me even write it. And now I'm going to is defined by ODE on the tangent bundle. See the equations above. So, namely, this equation here it's a very simple equation.
What does it mean to be defined on the tangent bundle?
What?
So if it's defined on the tangent bundle, it means that the solutions will be in the tangent bundle?
It means the solutions are curves on the tangent bundle. I'm glad she's asking me these embarrassing questions always, because they're good questions. The solutions of the ODE are curves on the tangent bundle. I mean, I said it. Just like here, the solutions of this stupid, it's not stupid, this ODE, the solutions are on the tangent bundle of the real numbers.
So does that mean that the solutions will be a section of the tangent bundle?
No! But you're close. The solutions are curves. So you can't expect that. But what you can expect is this. So I'm going to explain what you just said. Okay? I have to draw a three-dimensional picture, if you don't mind. I'll try. Oh well, okay. So there's the tangent space. There's the tangent space of 1, 5. Here are the tangents. Aha. Ah, yeah. Now the color helps, doesn't it? So here we go with the 0 section. M, okay, and this is the 0 section of the tangent bundle, okay, and now, I told you, I'm trying to push the importance of the tangent bundle, and the tangent bundle, well, let's say I don't have any canonical structure, but I will find some canonical structure here. You were interested in sphere bundles, and you have a unit sphere here. If you add a metric to this bundle, and we will have metrics in this bundle, so you will see that there really is a unit sphere bundle here going on in the background. We can always take a metric, and we will always have some interesting sphere bundle available. And so you have the good picture that Maria was asking me to draw for you. You weren't asking, but that's probably what you meant. So you have the tangent bundle, you have the ODE on the tangent bundle, and in fact, one of the key facts which I'm going to mention almost immediately is that in fact there will be in our considerations an invariant sphere bundle for the flow. So this is an ODE, and there will be an invariant sphere bundle when we have a metric. We don't have it yet, but now that's not. I drew a picture of the flow. Okay, that's maybe maybe an integral curve of this thing. But what can happen, as you know, is there's no reason that this flow doesn't come back here and come back like that. Right? There's no reason. A flow is a global curve, it doesn't self-intersect. I mean, it's an orbit of a group, right? It doesn't self-intersect. But if I draw the picture here as a surface, and look at the flow that we really want, which you think about geodesic flow as being in the manifold itself, you start flowing here locally, this is good, but you may flow back. Right? Because it's the projected flow. So the real flow that God gave us really is in the tangent bundle, and it's a flow, an action of a one parameter group, local, many times global. Yeah? Right? And its projected thing may be something like this. Right? I'll give you an example of projected things like that, is a periodic orbit. Some geodesics, as you know and believe, should be periodic orbits. And it's a very interesting thing, speaking of Arnold, to understand what periodic orbits really mean. If you have a torus, oh, excuse-moi. You have a torus, a geodesic, you believe will be something like that, right? You know it should be like that because this thing is a quotient of linear stuff, and that should be, the metric should be the flat metric because it's just a quotient metric. So it's the image of one of these things, and so it's like that. So a periodic orbit downstairs, okay, it doesn't self-intersect terribly like that, but it's periodic. But upstairs it's not periodic, it just comes back and comes back, right? It's just, right? It comes back here and comes to a different point there, and then goes on, comes to a different point there, goes on, and so on. Okay? It's a beautiful picture, right? Okay. Geodesic flow is really on the tangent bundle. There's a first order ODE, that's what you were asking. And the second order ODE describes the motion on the manifold, describes what I call connection geodesics. Okay? Okay. Now that is your author definition of geodesic. It is not my definition of geodesic. I like it, but I will now give another definition of geodesic. So geodesics, in terms of length, I mean, I think that's what we all think of when we think of geodesic, the shortest curve, length of the shortest curve, right? So the setup that we have here is we have G's on a Riemannian manifold. So when I have Riemannian manifold, I write it like that. I try, if possible, to let the metric be denoted by G for Gauss. So that's the Riemannian manifold. So Riemannian. Some of you are interested in pseudo-Riemannian case, so this is much more delicate. But here I'm in the Riemannian case, the positive definite. And so, in deference to the naive mathematician, we will first define a mathematical notion. It's called the length functional. Of a curve. So the length of gamma. Anytime, some of you are learning real analysis now, anytime you hear the word functional, it means a linear function on an infinite dimensional space. It's crazy, it's just a linear function on some space, but when you hear the word functional, the author or the teacher is probably telling you about a linear function on some infinite dimensional space. And of course, the space of curves is really infinite dimensional, space of smooth curves. So the length is going to be a functional on the space of curves. Maybe not linear, but a function. And this length function is simply defined, curve is going from A to B, as what it should be. Everybody learns this in calculus. It should be you add up the derivatives and you get the length, right? Now this norm is unfortunately in local coordinates a square root of something, right? You learned it in calculus. It was terrible. I even wrote something about it when I wrote a note to you. When I first saw this in calculus, I saw this. You probably all saw that. I know, what are they talking about ds squared and square root of ds squared? It has no meaning whatsoever. Right? Right? You can, yeah, it means nothing. Well, of course what it means is you have, let's say what it means, you have a Riemannian metric on the tangent bundle of wherever you're discussing this matter. And if you have a tangent vector, that's a tangent vector, you know how to take the norm of it. So you take the norm of the tangent vector and integrate it. Now we know. But we know, that's typical. We learn it too late. We had to put up with this terrible thing. It's terrible. Okay? Right? That's what it is. You okay? So, okay? So that's the length functional. And this is terrible, but there's something else that's much better. But it's different. At least at first it's different, but in the end it's not different. So this thing I denote by E, and this is even called in the mathematics community the energy of this. But in the physics community, to bow to you people in physics, it's called the action. Okay? And the integral of this action is scaled for some reason that we don't know. Squared. First of all, this has to do with physics, right? I mean, this has to do with physics, and we call this energy. So this is either the energy or action.
Is it also functional?
Huh?
Can you also say that it's the energy functional?
Energy functional on the space of curve. Energy functional on the space of curve. Or the action functional on the space of curve. And in this case, what we have here, both people call this Lagrangian. As I said, it's best to copy the notation of the physics community. It's always the best notation. Now I want to indicate some really interesting point. A key confusing point is, at least for me at the beginning of the subject, is that gamma depends on the parameterization. Right? Gamma is a mapping from an interval to a manifold, and if I apply diffeomorphism, let me write it here as a picture. You have a manifold, and here's this image curve gamma, and it's a mapping here from A to B, and if you have this as a mapping gamma, and if you apply diffeomorphism, you should always have this picture. I tell the beginning students, always draw this picture of change of variables. This is the right picture of change of variables. Say phi. If you have a diffeomorphism from some other interval to AB, you get the same curve. Right? This curve here is gamma composed of phi. It's really the same curve. And so, also as you learn calculus, it's a good idea to choose a particular parameterization. And if this curve is smooth, which means in particular we're looking at a local situation now, if the curve is smooth, the velocity vector never vanishes. It may increase and decrease and increase and decrease and so on. But what we can do is choose the parameterization by arc length. Right? You can do that. Right? In other words, you have a change of variables. This is maybe an S space and this is a T space. You make this change of variables from T to S, and now S parameterized by arc length. This means the stupid thing that the length of this thing is always 1. Right? That's what it means. Right? That means that these two integrals are up to a constant the same. Okay? This means that the physicists, as usual, are right. We don't need to look at the square root of this thing. We can look at the Lagrangian and the action, because it's the same for R. Yeah. You don't like that.
How would you choose such a parameterization? Like, what's different? What makes the how does the parameterization change the length of, like, the norm squared G? It's the same curve.
She's very, very asking these terrible questions, which I'm not mad. I'm just resting because you tell me this terrible question. How does changing the parameterization have anything to do with this? It certainly has to do with a curve. It changes the curve. Come on, a curve is a map, is a map, is a map. I've said a million times, a curve is a map. If you don't write a curve, if you think of a curve as just some image guy running around having fun, you're wrong. A curve is a map. Now, this means, for example, if you're driving Formula One, the first Formula One race will be in Melbourne this weekend. Oh, today's Friday. Tomorrow the trials in Melbourne. I don't know, I'll be very interested to see if Leclerc does well with Ferrari. I don't know, I watched it. So, if you have Sebastian Vettel, you maybe know Sebastian Vettel, he's the German great driver, goes slow around the first thing and then goes incredibly fast along the back, and his Ferrari goes 330 and then comes to the slow curve, sometimes 60, and then so on. He's changing his velocity, but the curve is the curve is the curve is the curve. In terms of the image, right? So you should take the bloody parameterization out of the picture. right? You should parameterize by unit velocity. Or constant velocity at least. That would help. So Fettel has a certain non-constant velocity going around this curve thing. And I will get there and drive, no, I can't drive. He will go 330 in here, 80 and so on. But I will drive, no, I won't make it, but I would drive maybe 220 or 2 something like this. I used to have a fast car. And it's clear, right? So we take parameterization out of the picture and make unit parameterization, which we can do. Right? The parameter is the arc length. So the point S that parameterizes the point on the curve is the length from the 0 point to that point. Yeah? Okay. And now Maria asked this question. What happens? It should not have, I'm answering your question now, or making precise your remark. I mean, you believe it. Right? You better believe it, because we're parameterizing length. And it should not have to do with parameterization. And this is a trivial calculation. You just put in change of variables and do the calculation. You've probably done this before sometime. Right? So that's great. So that means that the length functional and the energy functional, or the action functional, are the same on essential curves. So this means we go to minimizing the energy integral, or action integral. Right? And it's a heck of a lot better to do that with that square there, for one thing. And it turns out, conceptually, it's also better. So this is the thing to consider. The energy integral or action integral. So again, the physicists were right. They know that. Okay, so we do, we begin as a child. And I teach many courses, including courses for children. For example, Applied Calculus 1. Well, and then they go on to make money, and I'm a poor high school college teacher and so on. They go on to the finance industry and make millions. Right. Or high school. German people know all about this high school stuff. We begin as a child, find, set. So we have a function. Here's x, and here's some function here, and we're looking for this point here. Here's x, and this should be the derivative of x equals, so this is a function f, and you try to find f, derivative of f equals 0. Right? Now, there are always two things. There are no Germans here today. Oh, yes, the college are German, sort of. Yeah. It's called Kurvendiskussion, yeah? You discuss curves, and the first thing you do is you find the zeros of the derivative, and then you find the endpoints, because maybe the minimum or maximum is taken at the endpoint, and then you check all three things and try to find the minimum, right? Right. But for a bit older child, you check this thing second derivative out. Right? There's a good reason to check this second derivative out. Right? You write down the Taylor expansion of the function to third order, and you see that the second derivative, if it's non-zero, will tell you what's going on. Right? If everything vanishes, you have something vanishing in third order, it's very delicate, right? But you write down the Taylor series to second order, you get that. And if you know that this thing is positive, then that means a minimum. we will not do this here, but in fact, the second derivative test here, but in fact, you can do it. Okay? We will do only the first derivative, we only need the first derivative here. Okay? So we need to find critical points of the energy function. Critical points mean that this thing is 0. I have to talk here, but I will just say what I'm going to talk about this afternoon. So the general notation will be this. We will have an energy functional defined on some curve, gamma. I'm trying, so notation, I suggest you look at Arnauld. And here, his book on methods of mathematical physics. Is that what it's called, method of math physics? Hang on.
Classical mechanics.
Methods of what?
Classical mechanics.
Classical mechanics? Probably classical mechanics. Mathematical methods of classical mechanics, yes. And his notation, I will try to copy his notation. Maybe he calls this U. I'm not sure. I can't remember. There's always, for some dumb reason, a half here. The curve is defined on AB of something L, U, U prime, and T, dt. Does that look like good notation to you? Okay. Yes.
But, so if we say that so we choose the parameterization by an arclet, so the energy shouldn't be the integral from A to B of 1 dt, and then
That's what it is.
and then this would be minus A over 2, right?
That's right. So I don't care about the half.
So what
Well, if I minimize half of something, it's the same as minimizing something.
yes, but isn't that constant? I mean, you just choose your integral and then that's the energy then.
That's a trivial integral. It's a terrible thing, right? It's a completely trivial integral to compute, the integral of 1. Yeah, but you don't know the curve parameterized by arc length. Excusez-moi. Nobody knows this curve. We're trying to find the curve, actually, and you have to solve this ODE to find the curve, and then parameterize, yeah? Okay? So it looks crazy, but in fact, you see the point, right? Yeah. So this is the notion. This is the action or energy. U is a function of t, and this is called the Lagrangian. And now I will stop the lecture this afternoon, but let me warn you. Let me just tell you how confusing it is for mathematicians to look at this. This looks like a function of t. This looks like the derivative of the function of t. It is not. It is the variable u prime of t. Yes? Which, when you have a specific curve u, you put in the derivative for that variable. You got it? Do I need to... This is a very confusing thing that these people put on us, but they do it they do it not intentionally to confuse us, it's just to simplify matters. Those are three variables, u, u prime, and t. Okay? If you like, you can think of one of those variables as potential energy, and another one of those variables as kinetic energy. Right? Measuring in a system. And then you put a curve and then it measures it. Okay? Those are variables. They are not, when I compute, it's at certain points, when I put in a function, I will differentiate, right? Okay? So this is confusing. Maria, you will be really confused by this. Okay? When you read Arnold, you have to read Arnold. It's one of the most beautiful books you will ever read. These two books, you know, I seldom read books, but these two books I have read. It took me 1 month to read the first 80 pages of the book, and another 2 or 3 weeks to read the rest of about a 500-page book. The first 80 pages are serious classical mechanics in the sense of physics, and it's difficult. I strongly suggest you do it. Okay? So these are variables. This is the Lagrangian, and you're trying to minimize, you're trying to find the critical points of this thing. So we're trying to find the points where, whatever that means, the critical points of this thing, and I'll do this afternoon. Just find the critical points of this thing. This gives us the Lagrangian equations of classical mechanics, and this gives us, in this case, the Lagrangian equations of the geodesics, and using the Legendre transformation, which I will introduce this afternoon, this gives us the Hamiltonian equations of geodesics, or classical mechanics, which embeds all of classical mechanics in symplectic geometry, one of the most important modern subjects of mathematics. Let me say it again. Lagrangian, Hamiltonian, symplectic geometry. You have a question?
Yeah. It's not very clear to me why or how this, so this way we define a geodesic is based on the metric, whereas the previous way is based on the connection, and they should not be related.
Let's, you hear what he's saying? It's a very good question. We have two definitions, so let me just, since I've gone over, let me go over it a little bit more. So, critical points. What do you spell critical? Of the energy integral, so let me just write it as above. They are called Riemannian geodesics. For the obvious reason, because I use the Riemannian, this is your point, I use the Riemannian metric to define those geodesics, right? We will see maybe I put in here, thank God, if the answer to your question is that the ODEs are the same. Of the action integral, the same. As the ODE for the connection integral. Now the point that you're making is that we now have an ODE that really, in some sense, generalizes the naive ODE for geodesics, right? Or for any connection. So in some sense, it shows you really the right thing to consider as a connection, right? From the point of view of the ODE. Okay. is very interesting. Okay, see you this afternoon.